There you go. These are the harder ones. Okay, yesterday was warm up. Yesterday we learned how to solve for A, which isn't really solving. It's just plugging in numbers and hitting enter on your calculator. And then we learned how to solve for P, which is where we divide both sides by all the stuff in the formula that's attached to P, which if you know how to use your calculator is pretty straightforward. These two methods today are harder. So what's left is to solve for R and to solve for T. We will never solve for N. I think, as I said, maybe I didn't say this yesterday, I don't know how to solve for N, and it's not out of ignorance. I've Googled it a dozen, 24 times, and it seems to be even crazy upper level college mathematicians. The process of solving for N is beyond description, beyond reasonable doability. So we do not solve for N. I will not obviously ask you to do something that I don't even know how to do myself. So we have to be really good at solving for A, solving for P, that was yesterday. And then today we learn how to solve for R and to solve for T. And then hopefully we'll get some work time today, and of course a whole bunch of work time tomorrow and potentially Thursday as well. So, well, you see what's going on here is I'm giving you the principal investment value. I'm giving you the final amount. I'm giving you the frequency, the N value for the compounding, and I'm giving you the time, 30 years. And what we're after here is what interest rate would I need in order for starting money to become ending money. That's the goal. Pretty good. So you're going to have your formula handy at all times. It'll be committed to memory. If it already isn't, it will be by the end of today, I assure you of that. But remember, it's the final amount is equal to the principal amount times the quantity of 1 plus the interest rate divided by the number of compoundings per year raised to the power of the number of compoundings per year times the number of years. So that's your guy. And as I like to do, don't know that everyone else will or does, but I like to make a list, like of the cast of characters. And so I say to myself as I go through, I list the things that I know. So what is 5,000 going to take the place of? Right, so P is the number 5,000. The next thing I see, well, I'll let you tell me, what else is from the paragraph pertinent? A is given for sure. What's that? And then what else? T is what? And what else is given to us? It's not given as a number. I'll say again. It's the N value, and I will always give you that. If I haven't made that clear, I will always give you the N value. Like that's 100% of the time. You're onto something there. It's the number of times per year that the interest compounds. And since it's monthly, then we infer from that. It's not really an inference. I mean, it's just given that it happens 12 times then per year. There are 5 variables in this formula. I'll always give you 4. If we go to the continuous compounding, the PERT formula, I'll always give you 3 because there are 4 variables. So we'll always give you however many variables there are minus 1. And then that minus 1 is, of course, the one that we'll solve for. So step 1 is always to plug the numbers into the formula and then take a look at it. So if we recopy that white formula down, putting numbers in place of letters, we get 79,000 equals 5,000 times the quantity of 1 plus what? R over 12, good job, to the power of 360. Very good. Any questions so far? You people that are really good at math have learned, you've cracked the code. You understand that there are very specific steps generally that we have to follow. We can't go rogue. We can't veer. Math isn't generally like that. You don't get a lot of freedom of expression here. So follow these steps really closely. You've seen this idea before, and you've heard me say this before, not necessarily in this context, but this thing, in case you don't remember, is called the power. And the power generally needs to be isolated because we're going to have to undo the power, but we're not ready yet. So how would I get that yellow thing by itself? Divide. Certainly subtraction would do us no good because the 5,000 is not added, right? It's not a separated term. It's a multiplied term, so we have to divide both sides by 5,000. When we do that, on the left-hand side, I'm going to write this down, and then I'll just kind of hesitate or pause for a moment while you guys all come to grips with why I wrote what I wrote. If you take your calculator right now and divide 79 by 5, you're welcome to. You'll get a decimal, obviously, duh, because it ends in a 9. But in this case, is it the kind of decimal that we would steer clear of? It's not, is it? It's a friendly decimal. So whereas I might leave mine as 79/5, you might look at it and say, what is that, 15.8? Is that right? So I have no issues, as I've said before, if you put a decimal over there, because it's not the kind of decimal that's going to keep us up at night. It's not going to, we're not going to lose any accuracy. So you can leave it as 79/5, or in a case like this, you can put 15.8. Don't ask me which is better, because my answer will, of course, be I don't care. I do care when the decimal's ugly. But if it's like this, 6 of one, half dozen the other, no one cares. All right, and then on the right side, we've now isolated our power. So we have 1 plus r over 12 to the power of 360. And no one's ever asked you to solve an equation like this before. I was your algebra teacher. I'm your algebra 2 teacher. I would generally be the guy that would ask you to do something like this, and I never have. Any ideas as to how we can make some progress? Listen, that R right now is hidden well. He is well protected in a bunker. We can't go and say things like, let's subtract 1 or let's multiply by 12. All that stuff in parentheses is completely off limits. But it wouldn't be if we could get rid of the parentheses. And the parentheses only exist because of this guy. If it wasn't for him, we wouldn't have parentheses and everybody would be free to move about the cabin. Any big brain thoughts on how we can kill a huge exponent like that? No, I wish we could. Distribution doesn't work over addition problems like this. Great thought, but no. Huh, say again? Root? What kind of root? Nope. Nope. Yes. Yes. And as weird and ridiculous as that sounds, for the first time ever in your math life, you're about to use your calculator to take the 360th root of something. Exponents can always be killed by their corresponding roots. If you see a square, you square root. You see a cube, you cube root. Well, if you see a 360th power, you 360th root. And you got to really, this will probably be another pause the video moment coming up here, because it's going to take us a few minutes to everybody figure out how to put in a 360th root on your calculator. If it's a scientific calculator, though, it will do it. So what winds up happening is over here on the right-hand side, I'm going to take the 360th root, and what I'm going to get is this. That's how this works. If you apply a root to a corresponding power, they perfectly, cleanly, inversely kill each other, dropping, and everyone is now free to move about the cabin. But the issue now is that on the left side, I have the 360th root of 15.8. I mean, think about that. The math gods are asking you, not me, the math gods are asking you, what number would you have to raise to the 360th power to make 15.8? Yeah, I don't know. And so somewhere on your calculator, depending on what model you have a button that says like this. And I'll, again, pause here and give everyone a chance to find that, because I don't want to waste video time on this. But now that you found that button, then you're going to type 15.8 in over here. And you and I are going to come to an agreement that what we see on our screen, I don't care how many times you do this problem, it isn't going to be pretty, is it? So what we want to do is not put that on our paper. We know that we lose accuracy if we take, by the way, what did it come out to be? Here, I should just do it real quick. Hang on a second. My calculator screen is showing me 1.007696.159, right? So the worst thing we could do right now is copy that down and say, oh, it's about 1.01. Don't do that. That's bad, right? Remember, leave the accuracy as intact as possible until the very last moment. We should only ever round at the very end. And so what I would like to do with a modern calculator like this is let's think about the algebra of this now. So if I have this ugly number on the left-hand side, go back all the way to what you know from like 8th and 9th grade and ask yourself, if I had an equation like this, say I had something simple like 4 equals 3 plus x over 2. I mean, forget that this is algebra 2 and forget that we're solving these complex problems. Just the red equation, what would you do first? What would your instincts tell you to do? Right. You just know that. You know to subtract 3 first, right? And then what would you do after that? You would times 2. So follow that exact same algebraic thinking and just let your calculator do all the heavy lifting. Let it lug the numbers around for you. So while you have that 1.007696 whatever, blah, blah, blah on your screen, in this problem, what are we going to do first? -1. So with that number on your screen, just hit -1. And it'll always, it knows, these new calculators know to take the 1 away from the last thing you did. And then make sure you hit enter. Not like that was a big shock. You knew that was just going to take the 1 off the front. And now with it on your screen, what are you going to type in next? Times 12. Very good. So with that number on your screen, hit times 12, hit enter, and voila, there is your answer. So when we talk about rounding, I'm a big fan of 2 decimal places. When I get to have a say in it, which on my worksheets I do, Delta Math, sometimes I don't get to boss you around, but I like 2 decimal places, and most people do. And so I look at that, I move the decimal 2 places to the right. And if I do that, it would say 9.23539035. So my answer is going to be the interest rate required is around 9.24%. So we just backtracked and figured out using some pretty cool math what interest rate would be required to turn money A into money B given some conditions. The good thing for you, I mean, I let you use notes, and so to not have them is inexcusable, but if you're a kind of minimalist notes person, you can always remember this association that when we're solving for R, we use a root, and they both, you know, are root. So that might help you to memorize what to do. Got it? That's the process. Now we have one more problem, and then I got to talk about a little weird example, and then we're going to have a ton of work time coming up. So here's the next example for your notes. I'll pause it for a minute or so. Running. So as you read that problem, you're going to go through and pull out variable values. You're just going to take them. You can take them in any particular order. It doesn't matter as long as you identify them as who they are. So what's the very first thing that we cross paths with? $7,000. And what is that going to take place of? Very good. So P is going to be replaced by the number 7,000. What's the next thing we encounter? What's that going to take the place of? Good. That's A. That's my final amount after the end of the problem. So A is going to be 100,000. What's the next thing we encounter? 5.85%, which is the rate. And how do I write that down?
0.0.
Good job. 0.0585. And then the last thing, as generally will be the case, we encounter a number that's not really a number. It's going to be n. And what's n? 4. Quarterly means 4 times per year, once per quarter. So into the formula, we'll put our values. And this time we'll notice that the variable that we're trying to solve for is in a very familiar location, something that we already know how to do, thankfully. And this is why we learn logarithms and other types of exponential equations before we embark on this little unit. You'll see. If you haven't already written it down, you'll see soon. So in place of A, we put 100 grand. And we put equals P, which we replace with 7 grand. And then in our parentheses, we put 1 plus 0.0585 divided by 4 raised to the power of 4 times t. Before we learned about logarithms, we would not be able to solve this equation. I hate to say that, it sounds kind of mean, but like you can't solve this unless you sit around and just guess and check for like hours. So remember, logarithms are our tool that we use when there's a variable nanny boo-booing us from up high in the exponent. And so step 1, as has been the case, is to identify this. Remember, that's called the power, and we want to get the power by itself. That's a pretty common theme here. So what do we do first? Divide both sides by 7,000. And so if I think about division, I know that dividing by anything that ends in 3 zeros means that I can take 3 zeros off of the top number and then just write the bottom number as a 7. So what it looks like as a fraction would be 100 sevenths. That's just 100,000 divided by 7,000. Kill the common zeros and you're left with that. If you divide this one into your calculator, you'll see this time that we don't want to go the decimal route. If I haven't made that point clear, I am terrible at my words. Remember, that's a decimal that we go, whoa, no thanks. So we leave it as 100 over 7. It's all good. And then on the right-hand side, we now have our power by itself. We have 1 plus 0.0585 divided by 4 raised to the power of 4t. It's the moment of truth. Two kinds of people in this world, people that would look at this and say, I don't know what to do, and people that say, I got this. Who's our guy? What's our go-to? What do we have to do? You have to log both sides. Anytime this happens, listen, if you learn 5 things from me this year, let this be one of them. As you go into the ACT and whatever college math classes you take, when the exponent is where the variable hides, you need to log to get the exponent down, the variable down. If he's going to hide from you up there, you're powerless. But as soon as you apply a logarithm to both sides, it's open season. And so we're going to log both sides. There's no way around using a logarithm in this case. And so I'm going to log the left-hand side and call it the log of 100 sevenths. And now on the right-hand side, I'm going to multitask. I'm going to bring the 4t down in front, and I'm bringing it down in the front of the log of the quantity 1 plus 0.0585 divided by 4. I'm saying, like, again, I try to be honest with you. 5 things. If you walk out of here in May with 5 things, let that be one. Empower yourself by saying, I know how to solve an equation like that. And so Mission accomplished. The T is now scared. The T was not, it was nanny boo-booing us when it was safe up in the tree branch. And now it's like, I got you, bud. And so what we think about now is, okay, to get the T alone, we have to kill this 4 and we have to kill this log. And again, with careful use of a calculator, we can get this done. We can get it done in one step. We understand the algebra just simply says, I got to divide both sides by both yellow boxes. And so what it's going to look like when I type it into my calculator, I'll write a long stream of text here so you can see what it should look like, is I'm going to hit the log button. It's going to open parentheses. I'm going to type in 100. I'm going to hit divided by 7. I'm going to close the parentheses, and then I'm going to hit divided by. And we had a conversation about this about a week ago. It was inspired by a question that came from over here. I gave you my thoughts on how to do this, and someone had said, can I do it as like a division and then another division? And the answer is either way. The way I like to do this is I like to just put a new set of parentheses like this, right? And I can't really close that one yet on my calculator, but I start a new set. And that's my way of telling my calculator, hey, all the stuff that's going to go in here is going to be done first before you do this division sign. So hold off. And so inside of that, I'm going to type 4, and then I'm going to hit log, and it's going to open a set of log parentheses, at which point I'm going to do 1 plus 0.0585. I'm going to divide by 4, and then I'm going to close that parentheses, that set, and then I have to close again to tell the calculator, hey, I'm done screwing around in the bottom of the fraction. You're good to go. So just give me a quick second. I was too busy talking and I didn't type it in myself. I hope you got what I got. Well, I hope what I got is right. I came up with time is approximately 45.79 years. Does that match with what you got? Any questions on that? You're going to have questions over the next few days. There's one more example and then I'm done. Sorry, it's been a long couple of days, lots and lots of notes, but there'll be lots and lots of work time on the tail end. So you now know all of the processes. The only exception now is that there will be instances, like you can't now go in your notes and say this. To solve for R, I always use a root. And I know I kind of said that earlier and I kind of wish I had that back because in the example I'm about to give you, that's not necessarily true. So one more example for you to write down and then I'll not torment you with these long examples that you have to manuscript in anymore. So, R is generally the hardest one for people. The fun thing about P is that no matter if it's continuous compounding or periodic compounding, you do P the same every time. T, you do the same every time. A, you do the same every time. R, people that are good at taking notes, you will specify this in your notes. The method that you use to solve for R will be different depending upon if it's continuous compounding or periodic compounding. Because we got to use a different formula. And the R, as if you're paying attention here, thinking ahead, the R is located somewhere else in the continuous formula. So at the end of class yesterday, or somewhere near the end of class yesterday, you were given a formula for continuous compounding. And you might recall I called it the PERT formula. And so the PERT formula says that the amount of money we'll have in our account is equal to the principal investment times E to the power of RT. So that's PERT. For variables, we got to go and dig out 3. So let's go through them, hit them in any order you want. What's the first thing that catches our eye? 35, and that's what? Good job. So P will be 3,500. What's the next thing that we catch? A is 145,000. Good. And we do have T, right? Remember, N would generally be given to you. It just doesn't apply in a continuous compounding situation because N is infinity. It's infinitely many times per year. And so what's T is 40, right? All right, we're going to plug these numbers in and get the ball rolling here. So in place of A, we're going to put the final value, which is 145,000. In place of P, we're going to put the initial investment, which is 3,500. In place of E, we're going to put E. It's not a variable. In place of R, we're going to put R, and in T, we're going to put 40. So the exponent now says 40T. I don't want to write T40 or, you know, the other way around. Did I say that right? So, or what would that say? R40? How did I put T? Sorry, that's 40R. Please don't write that down. Fix that. I thought that came out wrong. I don't want to write R40. That sounds like something weird. I don't know, like a kitchen cleaning solution, like use R40 on your tough lime stains or something. So what do we do? You know this. I don't have to tell you this. What do we do first? Divide by 3,500. And again, and again, that yellow thing is called the power, and you want to get the power by itself. And so if I divide both sides by 3,500 on the left-hand side, if I could take off a couple of zeros, I'm at least left with 1,450 divided by 35. I have a sneaking suspicion that this one might come out nice. Let's take a look. I really don't know. 1,450 divided by 35. I was wrong. It does not come out nice. So let's just leave it like it is. If you want to divide them and reduce them both by 5, whatever, get down with your bad self. Because the calculator is going to do it all, doesn't matter. No benefit. So let's leave it like that. And then this equals E to the power of 40R. We were a little slow on this answer earlier, 8 minutes ago. Let's try again. What are we going to do? Nope. I need to do better. I need to do better at getting my point across. Do you see the variable? You see it, right? Where is it? It's in an exponent. And Balin, how do we get an exponent down? We log. Don't take that like maybe some of the time I'll take this advice. I'm telling you, when your variable is hiding in an exponent, you're going to need to log both sides. The log doesn't work until we get the power by itself. That's what that first step was for. The division by 35 happened to make what's about to happen possible. So if I log both sides, I want you to take note of something that I'm going to do up here on the television. I'm going to natural log both sides. I'm going to do the natural log of 1,450 divided by 35 is equal to 40R times the natural log of E. I'm going to ask this question even though I know you know the answer. It's almost rhetorical. Why did I natural log? Because the natural log of E is 1. And anything I can do to save myself having to push more buttons on my calculator, sign me up for that. And so by choosing a natural log in a problem like this, I have effectively made this thing that I'm crossing out pointless. And the algebra becomes a lot simpler. You should always use a natural log in any instance where there's an E involved. It's a benefit. And so what I really wind up having to type in is a lot is a lot simpler than what I did on the last problem because they don't have any complexities on the right-hand side. So we wind up just having to type in the natural log of 1,450 divided by 35, close parentheses, hit divided by, are you kidding me? 40. Nice and clean, nice and simple. So natural log of 1450 divided by 35, close it down, divided by 40. Move the decimal 2 places to the right, and what do you get? Perfection, 9.31%. So you now have instances in your notes, and you can clean up your notes as you see fit, of solving for A, solving for P, solving for R, solving for T, and also solving for R in the continuous formula. Got it? Now comes the fun part. I'm going to throw a bunch of problems at you, and you get to flex on my worksheet and say, I got this. It's going to take some collaboration, some question answer. Some advice I can give you before I hand it out is this. At the beginning of each problem, you should write down the formula. I think it helps just to see it, and then write down that cast of characters, write down everything you know, and from there, you get stuck, I'll give you a hand.